Um, for our last session before lunch, we are going to spice things up a bit. Well, a little bit of a throwback to the Year of Lightning talks. So for this next presentation, we have two speakers, each for 10 minutes. So we have Rodrigo Bersa from AWS. He's a solutions architect there. And then immediately following, we'll have Zemicheal. He's at NVIDIA as an applied researcher. And their talk today combines two parts of one solution for LLM agents for vulnerability identification and verification of CVEs. Thanks.
Hey, hi everyone. For those who don't know me, my name is Rodrigo Bersa. I'm a specialist solutions architect for containers at AWS. So I work a lot of like Kubernetes and container and building images. And like earlier this year, we started talking about like, hey, how can we improve the verification of vulnerabilities on container-based images and shifting left to avoid like that we have like so many production environments with exploits and things that can compromise our environments. So we started doing like a small research about that, and we found some alarming numbers that vulnerabilities are exponentially growing, and the prediction for this year is to increase like 25%. And we have like this big number of like 2,900 vulnerabilities found per month. That's almost one per day. And if we drop, like strip down to minutes, we have like one vulnerability found every 17 minutes. So this is like very alarming. Imagine how many production environments, how many products we have vulnerable outside in the world. And this becomes even more concerning if we take a look on the next part of the research. We found that the time to solve a found vulnerability is almost 2 months. So the mean time to remediation, or MTTR, it's 58 days. It's like if you think about like there's one vulnerability every 17 minutes, and we take 2 months to fix. This is like very, very alarming. And together with that, like we found information that like the attacks on 2020 was 70% with more than 2 years old vulnerability. So the vulnerability was running on those environments for all of this time. And like, we don't have like frequent scanning. And then we start, hey, what's the impact of that? Like, of course, we have like outages, we can have like things compromised. But if we're talking about costs, for example, the cost to fix a vulnerability found on a production environment is 640 times more expensive than if we found in early stages, like development phases. Because if we found on the development phases, what we need just a few more hours to implement the fix or to correct that vulnerability. Other than in a production side, we have outages, we need to stop production, we impact our customers, our users, and this is like very, very, very expensive. And why this is taking so long, and why do we take so long to find vulnerabilities and to fix those vulnerabilities? So this is the traditional management for vulnerabilities. We have like the vulnerability identification that we'll talk a little bit more later. And then we have the analysis and the risk assessment. And this is a very laborious part. We need to understand, hey, is this vulnerability impacting my environment? Is this exploitable, or is just there? We're not like exposing that anyway. And then just there, we start working on the remediation, and we need to do like a lot of corrections, maybe like I said, on production running environments that will impact everybody, every customer. And then going back to the vulnerability identification, like who's responsible for doing all of those tasks, right? So probably we have like analysis and risk assessment for a security engineer, and the remediation will go be like a shared responsibility between a security engineer and a developer that will need to apply the fixes on the application, or maybe an operations team that will apply that on the infrastructure level. But whose responsibility is to identify the vulnerability. Should be on one of those teams, but if that's found like maybe in a production environment, our customer will find that, our users will find that. So this is not good, right? So this is the hardest part. Like how do we identify that vulnerability that should be responsibility of someone, but like this is like very prone to errors, need like very deep analysis and very time consuming. It's a boring process. And what did we envision to fix this boring process? So generative AI, use the power of LLMs and automated processes to fix that, like in advance, like shifting left to our building phase. Like automation and Gen AI are not just buzzwords, right? We need to reuse that. And also, we don't want to reinvent the wheel. We want to build a solution using existing things, existing products, and existing models to cover and fix all of those issues that we found, like on vulnerability management. Also, like the infrastructure to build like those can be serverless or container-based and event-driven. Like, what's event-driven? So if I found a vulnerability, what I'm triggering to fix that? I'm just finding it and reporting it, but what's the action that I'm taking like automatically to fix that, to create like a completely integrated experience for managing the vulnerabilities. So we using like generative AI and artificial intelligence to fix this part. We're basically started building the solution using two different tools. So I'm using here like for the identification, analysis, and risk assessment, this tool called Amazon Inspector. I'll talk about a little bit more about this. Why did we choose Amazon Inspector for that in a minute? But you can use like any open source tool like Trivi or Gripe or Claire to do this start to identify the vulnerability when you're building the image. The drawback of those solutions is most of them are local, so your developers need to have those installed and like run analysis on local machines before finishing building the application and pushing that to a container repository or package repository image like ECR, for example. So Amazon Inspector has this built-in integration that can do not just when you're building on the building phase, but it can continuously analyze all the existing images in your environment and say, hey, when you push this image, this was not vulnerable, but CVE just reported a new vulnerability that's found on that image that's already running in your environment. So this is like very important to not just, hey, it's not true that if I created an image that was not vulnerable, that it will not be vulnerable forever, right? So a new vulnerability can appear. And then we use generative AI to fix those found vulnerabilities based on reports or SBOMs that Amazon Inspector reported and created. So the first phase of our solution started like this. So we have like our code. We have like 3 different languages here, like Python, Java, and JavaScript. And then Amazon Inspector, we build our images, we push to a repository. Amazon Inspector can bring us like a report and another analysis of those detected vulnerabilities. And then we create a prompt on Amazon Bedrock or ChatGPT or any other available solution to say, hey, I have these vulnerabilities. How do I fix that? And then this tool could generate us like a pull request. Like these are the suggestions to fix. These are the packages that you need to update in your code to make those vulnerabilities remediated, right? So this was not really working as expected because every time we pushed a new vulnerability analysis or a new result, the model was just giving us, hey, like very long steps. Hey, you need to open your code. You need to do this. You need to do that. And we tested with several different language models like Titan. We tested with Llama, with Anthropic, Claude. And the one that was performing better was Llama 70B. And then we introduced what we call the in-context learning. So we provided the model, hey, this is more or less the result or the expected solution that I want. So we provided a few examples to do like the in-context learning. And then the model was like much more assertive on bringing us, hey, this is the PR that you need to open to fix this in your code. And the solution was just, after we have like the reports, it was receiving, creating the prompt, and then generating the PR for the specific repository to fix those found vulnerabilities. But then we started seeing that were just some drawbacks on that, because we were not able to patch anything that was running. We were just able to open PRs. We were not able, Amazon Inspector, for more that it can consult like databases and CVEs, it's not assertive on what's really exploitable on our environment. So these are some drawbacks. And also another thing is we need to provide like one specific model or in-context learning for each language that we want to publish. Like if I want to add like a new one, a Golang here, I will need to provide like a different prompt to fix the Golang found vulnerabilities. And then that's when we started talking with NVIDIA. And we published a blog post that will be available on the resources on the end of the presentation. And NVIDIA saw that, hey, I have the solution to fix all of those drawbacks that you're talking about. We have this new tool that's called Morpheus that can receive the inputs from your Amazon Inspector and like do like a very deep analysis on what are the vulnerabilities and how can we fix that like in the best way possible. And that's what like Ted will talk a little bit more about.
Yeah, so as we can see, the previous approach works mostly if we have patches. But in typical application, the availability of patches are kind of limited. If we see the report from 2023, for critical CVEs, the patch rate is like less than 60%. In fact, it's around 55%. This is actually very serious, considering the severity of the CVE. There are so many factors that affect this, including the software might not be easily patched. It could be an old software system, or the sector, such as maybe it's in the health sector or finance, might not be easy to do easy patching approach. There are also some cases where the software system is very interconnected with each other, and once you apply patch, it might cause havoc to the connected systems. So what do we do when patches are not available? So typically, when patches are not available, what cybersecurity analysts do is like it's a manual process, like starting from the information collection up to then investigation. Once the information are collected from across different external sources, such as blogs or security advisor boards, then they have to ask the container or the target system different questions to investigate the cause of the severity. Then once they kind of come up with a good solution or finding, they have to report as a standard format. Usually the standard format, like I think Lisa explained earlier from the CISA org, they provide it in terms of like VEX justification, like you have to provide them like kind of readable format or label format. So looking into this, we can understand one thing, like in this part, these can be easily or automated with the strength of the current LLM engines or the capability of the LLM. So how do we approach this one? Typically, a single LLM cannot do everything what we have explained, like starting from collection and then investigation up to reporting. So what we did is like we propose a multi-component LLM workflow, which includes starting from information collection up to report generation. So if we look in this part, for example, this one is the first component where checklists are created. These checks are basically the LLM gathers information regarding to the CVE and then creates a list of tasks that need to be done or that need to be asked to the target container. Then once we have these lists obtained from this LLM, we can include or we can give to another LLM, mostly LLM agent in this case, based on React agent, which is actually, which performs like actioning and reasoning behind the tasks. It creates responses to individual checklists. However, these checklists, they kind of only provide a list of answers. They don't provide any response like summarized response or a formatted response that could be useful for the downstream task. So what happened next is like, what if we collected this whole response or agentic response from the list and then reformatted into another format, like it could be summary format or it could be a VEX format. So to address this, we propose another LLM which takes inputs from the LLM planner agent, then reformatted into summary model or a summary information, which could be useful to a downstream task. Okay, so I don't want to overwhelm you with a big architecture, but we already talked individually little by little. So the way these things work is like we kind of split this whole system into 3 parts. I already mentioned that starting from the checklist generation up to LLM React agent, and then finally reporting, which is the summary we want or the VEX format. So this whole architecture are based on Morpheus pipeline, where Rodrigo mentioned it earlier. We use NVIDIA inference model for most of our LLM inferencing. We're gonna go through more in detail what kind of model we use, how do we evaluate this system. However, as you look into this whole component, it kind of contains so many components, and it's not like typical to evaluate, like similar to typical ML models where you have training and testing and you do run one phase of evaluation. Instead, what we did is like we set up evaluation frameworks, like we divided the whole component into several components, and then we evaluate individually. At the same time, we also did end-to-end evaluation, where we mostly did the evaluation at the summarization or the justification models. For this task, we basically use 2 types of data, like most similar experiments, like we tested first with synthetic data, then we create also a hand-level data, which is basically from target container, then we run all these workflows. Okay, so going into individual experiments, like the first part we experiment is like the checklist generation model. This is the first part where it creates the checks based the information collected from external resource. And this basically we experiment with 2 types of experiment, like how good is the prompts or the few-shot learning or with the zero-shot learning. So in order to evaluate this one, like I'm talking about these the last 2 plots, in order to evaluate this one, we came up with a good LLM judge matrix. But we also need to evaluate the LLM judge, how good is judging the experiment. So we measure the gap or the error gap of that LLM judge comparing to the human judge, which is leveled hand level from the analysis. We noticed that the performance or with the error gap is not quite big, especially with using the large model like GPT-4 and the Llama 3. We kind of get around less than 0.5%, which is reasonable looking into the whole pipeline. For the second experiment, we evaluate the efficiency or the performance of the React model, which is the main engine of the whole workflows. So for this, the goal is like how good are the different open source LLM models perform for the React question and answering tasks. We basically measure starting from the smaller model like Llama 8 up to Llama 70B. And we noticed that, excuse me, we noticed that using the larger model, like especially the 70B, has a better performance, both at the LLM judge performance as well as the ground truth, which is just measuring the accuracy of the response to the hand level response. With this, we decided that to go for the Llama 70B for most of our experimental works as going forward. So at the same time, we also did some experiments. Maybe I might not go in detail. We can refer to the paper, full paper, much more detail on this. This is basically, we also measure with some tools like we use internally for the LLM React agent, such as like code search tool, which we notice that very important, especially when you're looking into the fragment of codes or functions that are vulnerable in the repository. We noticed that the vector similarity search or based on the embedding might not be the best solution often, but sometimes you might need the exact search, or which is the classical lexical search. Finally, we perform the end-to-end evaluation, which is the measuring the accuracy at the justification and the classification stage. On this, in this first graph, we measure how good is the workflow at measuring the exploitability and prediction and the vulnerability task. We can see that we got around close to 75% on identifying whether this particular CV is vulnerable or exploitable, given all the inputs. This is reasonable looking into the many specialty components, such as the limited number of containers and the limited number of library information we get. At the same time, we further fine-tuned the experiment into looking into more categorical experiment. This is how about classifying the exemption, like exemptions, which means that if the analyst is going to provide reason for not flagging the CV as vulnerable or exploitable, he needs to provide some reason. Some of the reason include, like, it could be this require dependency to run or false positive, etc. So we measure also the performance of the models across these many different categories. We got closer around 93% for the vulnerable category, which is it's for us team is like the most important category. Whereas we also noticed that several degrade in performance when we look into the minor categories, like the exemption category. We noticed this one, the main cause of this performance degrade is mostly these classes are not well represented in the examples, and further upon looking, we are kind of enriching this, especially the borderlines, the classification borderline among many of the levels are not quite clear. Finally, I can leave you with the combined solution where Rodrigo explained earlier and the Morpheus solution combined together. So in the case when you have a patch, you don't need to run the whole workflow. You just only run the Amazon Spectre workflows. Whereas if you don't have patch, the whole system can integrate to work closely together, and it can help you in analyzing the CVEs. Okay, so what are the summary or the key finding for this whole work experiment? As you can see, I mean, this is a kind of giant workflows, and from running this experiment, we learned so many things. The first and the most important thing we learned is like LLM, or in particular, the LLM agents are quite good at identifying, especially could be helpful at identifying for the verification process, assuming that you provided enough input configurations, such as source code or documentation. In fact, you don't need to provide host level execution if you are looking more into configuration verifications. At the same time, we noticed that this workflow could be easily extendable. Assume you have extra information like operating system information or library information, you can easily extend this work. Same thing, we noticed few challenges such as testability and the evaluation case. Mostly this goes because due to the hallucination or the noise component introduced from one component to another component. And we also see some drawbacks, especially on the input of the CVs, like some CV, they don't even have much dense information, so that they cause so many missing information across the pipeline. So going forward, as a next step, our priority is like to test this further into latest model or larger model. Basically, the goal is like we are planning more into function call-based systems. So we are looking more models that can help us to use external function or external tools appropriately. One idea we are looking is like to convert all these LLM-based judgment into deterministic function, such as like could be different that could help us at the verification, including the dependency and version comparison functions. With this, finally also, there is one interesting idea we are looking for, which is exploring the code path exploitability. Basically, instead of looking at the function calls or the function availability, how about if you look from source to sink and trace back how the call is performed throughout the repository, and then try to flag it as appropriately. Okay, thank you, everyone. With this, I leave you the resource and demo used for these talks, and you can refer, including the blueprint from NVIDIA, as well as the AWS examples in GitHub. And yeah, thank you.
We have time for a couple questions in the back.
You can come, Rodrigo.
Oh, yeah.
Yes, that was a great talk. I wanted to ask if you guys did any work into going down to the nth degree of any of those dependencies that you found in any vulnerable sections of code, and if you actually found any, or if you did any work into finding the antidote to either patching or neutering any of the high probability vulnerable CVEs that you found. Thank you.
I can go for the first part. Like you asked about the dependency. Like the Morpheus pipeline is mostly works for the identifying and verification. For the dependency, we have some things we work on. Like for example, if you have a vulnerable CV, you don't only need to target that package, but you can also look further dependency on that package. One way we have already incorporated that tool because this React agent is very extensible and you can add many tools as you want. Like one way we extend this is by asking like external API like DevDop. You can get dependency information about the package and then utilize this information to further assess like if we have even that hierarchical like down and level dependency for that package.
So on the second question about like if we like did like the remediation and found like a common ground, like what we are fixing on the validation side that we did, we could like customize the prompt and the outputs on say, hey, if there's like a high it's a vulnerability that scored as high or critical, I want to patch like immediately on development environment. Like mostly of the tests that we did are related to upgrade packages on specific container images. Most of them are related to that, not for specific for code, because CVEs are usually found like on packages like publicly available. One other solution that we found was to maybe ask to replace the existing base image on the container, but this is like another level of conversation. For example, there are tools out there that provides us like 0 CVE base images, like ChainGuard, for example. You can download like a very like 0 CVE. If you don't install external packages, your image should be like secure by default. But but like I said, depending on the prompt, the language that the base image uses, we need to create like a different prompt, and this is like fully customizable. You can ask, hey, I want to fix anything, or I want to fix just critical ones and things like that.
Hi, thank you for the talk. That was interesting. Just a question because I noticed you had the context of enterprise scale, hopefully intended. And my experience is that much of the challenge is actually determining which systems are actually at the highest risk. So the criticality of the vulnerability is rarely the actual proxy for the risk, depending on the context of where that system sits. Is it internet facing or not? So when you go enterprise scale, have you considered a risk-based approach to add as another lens to this whole process versus just the the analysis of the system without, is it a crown jewel system? Is it internet facing, etc.? What other attributes are you planning in the future? Thank you.
Yeah, thank you for the question. It's really interesting. Yeah, so there are a few interesting Intel information we are adding. For example, from third-party Intel, like from Red Hat or could be from Ubuntu, depending on the operating system. We incorporate this one, especially at the gathering phase, like when we create the checklists, given the single CV ID, you can have so many information, even forums. But there are also some Intels we still trying to incorporate, like you mentioned that the severity or the criticality of the stage. The good thing is like this one is very extensible. Like we just need to only append the URL or the source of the information. But as for now, like mostly our case are like external, like related to the container, not like at the ranking phase of the criticality.
I don't want to keep anyone from lunch, but I had one last question. I know, so it seems like, for these complex scenarios, there's a really long tail, like you'll be chasing edge cases in this system forever. Have you found a reasonable approach to be confident in like some scenarios covered versus other scenarios, like you said, with the languages? And like, is there a way kind of to give more confidence to any of these outputs?
So for the first part, like we were just using like in context learning and the prompt. We did like some tests, like I mentioned, with different language models and using the in context learning. The findings were like very positive, and they were assertive. The only thing is that related to our last question is, we didn't know what's really exploitable, because even having the analysis on the vulnerability itself, we were not able to understand, hey, this is sitting in just a backend application. It's not exposing something. And that's where I think Morpheus can come into place to dive deeper on the analysis of that vulnerability and say, hey, this is vulnerable, but you're not exploiting it. So it may be critical, but you're not exposing that vulnerability. So you're safe in some way. You can like postpone the fix for this one and prioritize something that you're really exposing or are exploitable in your system.
Okay, awesome. Great. Okay, so we've made it through session 1. Thank you to our speakers.